I would like to welcome you to Lecture 13 on the topic of modelling and sensing. This lecture is part of the subject Future Farming Technologies, which is a component of the Bachelor of Agriculture and Technology. This degree is offered both at North Melbourne Institute of TAFE and at Melbourne Polytechnic. Please visit our website www.nmit.edu for further information on this course and the other courses that we offer. My name is Dr. Nikki Cooley. In this lecture today we are going to describe the concept of models with sensing. We're going to briefly look at their advantages and disadvantages, and we are going to look at some commercial systems. A commercial system that is currently in operation and some theoretical commercial systems. We will address 3 subject learning objectives in this lecture: 1, 3 and 5. So why put sensors with models? Well, once you have set up your model system, it may assist with your predictions, increase your accuracy to add a sensing component. This may increase the optimization of your farming system. Not only are you recording inputs of your farming system, but you are also interpreting them in some manner. The coupling of modeling and sensing opens up a huge amount of possibilities. Some of these are listed below. It offers the potential to add to new scientific insights into agriculture. I mean, a new level of our understanding of agriculture. This is particularly important for agriculture, as usually it operates across hierarchical structure, across space and time, and is very influenced by environmental ecosystems, for example, climate, soil, farm neighbour environment. A real-time dynamic model is enabled with sensing, and this allows optimization for any given climate, topographic interaction that your farming enterprise may occur. Coupling modelling with sensing allows for the potential of benchmarking and yield prediction to some enterprises. Sensing can increase the accuracy of the model as there are more data points to put into it. When you have sensors continuously supplying data and this data collection is thereby automatic, it allows for optimal time management. What I mean by this is you are not out collecting manual data for your model. You will ultimately increase the amount of information and the power that you can use that information. This will then potentially increase your accuracy, which would ideally lead to an increase in your economic outputs. I want to introduce to you now an example of a modelling system that incorporates real-time dynamic sensing. What we mean by real-time is data is captured as it occurs. The following is a model that enables the calculation of evaporative transpiration, which is often abbreviated to ET. This information can then be incorporated into an irrigation scheduling technology. The concept is simple. You have a weather station that produces a digital output. In this weather station, the array of sensors would include wind direction and speed, ambient temperature, rainfall, and humidity data. You link this weather station up to the model. It can be wireless, or the information can be sent through a cable, or the information can be sent via radio, as is in the system we describe here. The model is a set of algorithms that takes the climatic data and interprets into evaporative transpiration value. You can then mix your evaporative transpiration data value with some information about your crop stage of development and where you are in the season. And this can give you an automatic irrigation scheduling based on ET. Myself and a colleague, Dasa, worked on putting the calculation for ET with an irrigation commercial company mate together into a system that could incorporate all of the following. We collected sensor data and we modeled it in real time. I will talk about the outputs of this model more in the sensing section, which will be lecture 12. You can visit the website to see the details of the commercial product. There are several applications and enterprises that may in future be assisted greatly with coupling models with sensing data. I have suggested a few here. Real-time disease control in dairy cattle. If you were able to remotely sense the temperature of your cows, this could indicate the onset of mastitis. It is known that the cow's temperature can increase slightly before mastitis occurs. One could envisage a system where cow temperatures were remotely monitored using IR cameras, and then this data collated in a model. Inputs of the production could be entered also into this model, and not only could you allow for early disease detection, but you may be able to equate other important components such as quality and product control. There is great potential for coupling models with sensors for determining dynamic yield predictions. You could set up in situ sensors that are linked to computers. As the crop is growing, you could continuously update your yield predictions, both the date of your yield and your potential tonnage. And finally, there may be great advantages in coupling sensors of the soil with understanding the very complex soil environmental monitoring. Theories about how soil ecosystems could be coupled with soil sensors that could determine moisture, nutrient content, pH, EC, all simultaneously. This may enable us to understand, for example, better nutrient cycling, or understand better the leaching dynamics of a soil system. There are probably many more potential applications. This is just a quick summary of some of the ones that I thought might be possible. So there are, of course, some disadvantages to modeling coupling models with sensors. One is that both your model and or your sensor can be subject to error. You need to build in pathways that ensure that you check for such errors. For example, what happens if you're monitoring climate data and the sensor does not work for a short period? How do you manage the lack of data in your model? All of these things need to be considered and can skew the outcome of your model. Crop responses are subject to hierarchical systems. Therefore, sensors may be only indicating or biasing your model outputs. This is particularly important in agriculture, as agriculture is made up of many hierarchical systems. The influence of one cell all the way through to the environment. There are significant technical challenges which need to be addressed when you couple sensors with models. These are both in the way the data is communicated, but also in how the data is handled. There is a significant amount of data collected with real-time sensors, and this can cause some problems. There may be some model assumptions that are based on the accuracy of the data collection. That is, there may be an error in the temporal and/or spatial components of your sensing, which could lead to incorrect interpretations in your model. You need to be aware of these assumptions and be mindful of the outcomes. So to summarize the outcomes of Lecture 13, I think you should have understood now how one can couple sensing with modelling. You should see that there are many advantages and disadvantages to bringing together these two technological advances. I have given an example of a current commercial technological application and some possible future applications that may undertake this type of technology. This brings us to the end of this lecture, and in fact the end of the topics sensing and modelling. I'd like to end with a couple of quotes about some models. This allows a bit of reflection on what we have learned to date. George E.P. Bock said that all models are wrong, but some are useful. Albert Einstein said about models, make your theory as simple as possible, but no simpler. Albert Einstein also said, for every complex question, there is a simple and a wrong solution. A very mindful fact that we should take into account when thinking about models. This brings us to the end of this lecture.